Hello, everyone. This talk is going to be about the broadcast channel, which is a very popular and a very well-studied model that captures wireless communication. Wireless communication is in fashion, it is everywhere, but it is also prone to noise, and it is actually more noisy than communication over a standard wire. And as a consequence, research naturally focused on studying the noisy broadcast channel, where you want wireless communication that is resilient to the noise in the channel. A lot of work went into this direction. We have nice upper and lower bounds. And in this paper, what we want to consider is we want to consider a second aspect of the wireless channel, which is the presence of malicious parties. We say that wireless communication may happen over a large distributed system where there are n parties. And not all of these parties may be perfectly synchronized. Maybe some parties have some faults. Maybe some parties fail during the protocol, or maybe some parties are just malicious. And ideally, a protocol over a wireless channel or the broadcast channel should be resilient to both the noise in the channel, which is random, and the malicious parties, which may be adversarial. And this is how we want to do computation over the noisy broadcast channel. This is the main result of this paper. We show how to do computation over the noisy broadcast channel, even when there are malicious parties. But before I state this result more formally, let's just overview the definitions first. So the object of study will be the broadcast channel, and we will study the classic problem of bit exchange that was proposed by El-Gamal in 1987. The description is pretty simple. There are n parties. Each party I, has an input xi, and the goal of all the parties is to know all the input bits. So every party wants to output the vector x, which is x1, x2, all the way to xn. Now, in order to output this vector, they need to communicate between themselves, and this communication will proceed in synchronous rounds. In each round, we will have a fixed party, which is a speaker, and all the other parties will be listeners. And the speaker is restricted to transmit or broadcast the same bit to all the other parties. And this is actually the part where wireless comes in, because when you have a wireless router that is sending packets, then it does not really know the receiver. All it knows is that it's sending packets into the atmosphere, and everybody in this room will receive the same packet. So that's the wireless part. The same packet is sent to all the neighbors, all the parties. If the channel is noiseless, then this packet or this bit will be received directly. But if the channel is noisy, then there is some noise parameter epsilon, and with probability epsilon independently for each party, the bit that they receive will be flipped. And with the remaining probability 1 minus epsilon, the bit will be received directly. Okay, so how do you solve bit exchange over the broadcast channel? Turns out when there is no noise, then there is a simple n-round protocol. There are n parties. Each party simply takes 1 round to broadcast its bit. And because there is no noise, the broadcast will be received directly and everybody will solve bit exchange. When there is noise, there is a protocol that I'll call the trivial protocol or the naive protocol, where the parties simply broadcast their bit log n times instead of 1. And because each party broadcasts its bit log n times, the other parties can do majority decoding. And this will be correct except with probability polynomially small in n. Now, this probability is so small that you can union bound over all the bits and all the parties. And you get a protocol that takes n log n rounds or n log n bits of communication and solves bit exchange except with probability polynomially small in n. Can we do better? Yes, we can. There is a very clever protocol due to Gallagher, the study in a classic protocol from the 80s, and it takes only n log n rounds to solve bit exchange over the noisy channel. And this is actually an exponential improvement if you look at it in terms of the communication by one player. In the trivial protocol, a given player in this channel was sending log n bits. It was repeating its bit log n times, but Gallagher only requires it to repeat log n times. So it's an exponential improvement. And this is the best you can get. There is a matching lower bound that shows this is tight up to constant factors. But what this protocol has is this property that even if there's only one malicious party in this system, then this protocol completely breaks down. And in the presence of malicious parties, we will see why it breaks down later in the talk. But in the presence of malicious parties, the best protocol you have is the naive protocol where you repeat your bit login times. Our main result is that you can do better. Our main result is a quadratic improvement. We show that there is a protocol where each player communicates only square root login bits. There are some log factors that I will ignore. So the total communication is n times square root login. It solves bit exchange under the presence of noise, and even when up to half the parties are malicious. So let's first see, what does it mean to solve bit exchange when up to half the parties are malicious? Well, if there were no malicious parties, then usually solving bit exchange would require all the parties to output all the bits of all the other parties correctly with a very high probability, let's say 1 minus 1 or poly n. But in the presence of malicious parties, this requirement is too good to be true for two reasons. The first reason is that some parties are just malicious, and even if they cooperate perfectly, even if they follow the protocol correctly throughout the protocol, when it comes to outputting something, they may intentionally output the wrong thing. And thus, you cannot get all the parties to output the right thing, even if they are agreeing. And this is just because the malicious parties will output the wrong thing at the end of the protocol. So can we require all the honest parties or all the non-malicious parties to output the right thing? Well, it turns out even this is too much. And this is too much for a different reason. This is because throughout the protocol, a malicious party whose input is 0 may be pretending as if its input was a 1. And any non-malicious or any honest party cannot tell the difference. So you cannot expect an honest party to output correctly the bit of a malicious party. And you can also not expect a malicious party to output any bit correctly. So the strongest possible requirement that you can have is that all the honest parties output the bits of all the other honest parties correctly with high probability. This is the requirement that we work with. And we are able to get a protocol that satisfies this requirement, the strongest possible, in a computationally efficient way. By efficient, I mean that there are n parties and the algorithms that these parties run locally run in polynomial time. In fact, in our protocol, they run in near linear time, so that's very cool. But even above and beyond this theorem, our paper pushes a very important idea, which is that of property preserving interactive coding. Interactive coding is just a fancy term for making protocols resilient to noise. And what we say here is that there is a trivial protocol that is very wasteful in communication. It takes n log n rounds, but it has other nice properties. Because you simply repeat and you decode by majority, malicious parties do not really affect this protocol. Everybody is just doing their own thing. So it does not matter whether there are malicious parties or not. This protocol is also computationally efficient because all you need to do is to broadcast your bit and take majorities. And these are all nice properties that are there for this trivial protocol. And usually what interactive coding and noise resilient protocols have is they want to minimize the communication. They want a protocol that communicates as few bits as possible, but they're willing to compromise on all these other properties. What our theorem shows is that this compromise is not necessary. You can actually have a protocol that minimizes the communication. It is lower. It was n log n, now it's n square root log n. But it keeps all the other properties intact. So it's property preserving. This new protocol is also resilient to malicious players. It is also computationally efficient. And maybe if these properties are what you're after, then even if these properties are what you're after, you don't have to suffer the log n overhead. You can do a square root log n overhead. Okay, so that's pretty cool. And in the rest of this talk, I will talk about the ideas that go behind this theorem, and I'll actually present almost a complete proof with some minor calculations missing. And in order to start, let me first formalize the trivial protocol where players broadcast login times and decode by majority. I will use this to build up to Gallagher's protocol, and so it will be helpful in setting up notation. I want to view the trivial protocol as a two-stage process. I want the first stage to be where each player simply broadcasts its input login times. This is staged broadcast. And I want the second stage to be where players take the login copies that they heard from other players and then just do a decoding by majority. If they heard 0 more than they heard once, then they will say the bit of this player is 1. That's their guess. And if they heard ones more than they heard zeros, then they will guess that the bit of this player is 1. And because you repeated log n times, it works except with probability polynomially small, and you can union bound. So the trivial protocol works if you broadcast log n times. Now, the way Gallagher gets his improved protocol of log n is it uses the observation that not only do the parties correctly guess something that is correct except with probability polynomially small, the guesses of all the parties in the system are independent. And this independence stems from the fact that the noise is independent for all the parties in the system. How do we use this? Well, here's what Gallagher says. Gallagher says that in stage X, or in stage guess, you did something pretty cool. You were able to guess the inputs of all the other parties directly, except with probability polynomially small. And now what you want to do is you want to boost this guess so that it's correct except with probability exponentially small. How do you boost this? Well, you fix an error correcting code C that takes n bits, so it can encode the vector x, and it has constant rate. So let's say it outputs 10 n bits with some constant distance. And what the parties do is they all take the vector x that they computed in stage S and they encode it using C. So all of them have 10 n bits. Now, the first player broadcasts the first 10 bits of his encoding. The second player broadcasts the second 10 bits of his encoding. And all the way till the last player broadcasts the last 10 bits of his encoding. And basically what we did here is that if all the players agreed on this vector x, then together all they did was they broadcasted C of x, just that they broadcasted 10 coordinates each of C of x. But what is cool is that this broadcast was done using an error correcting code. So if you decode from this code, then even if a constant fraction of the coordinates are wrong, you can still decode correctly. And because players broadcasted an equal fraction of coordinates, a constant fraction of coordinates can only be wrong if a constant fraction of the players did not agree on x. Now, the probability that one player did not get x directly is polynomially small, but the probability that the constant fraction of players by Chernoff bound did not get x directly is exponentially small. There are n players, and by Chernoff bound, the probability that a constant fraction of these players did not get x directly will be exponentially small in n. And this is the boost that Gallagher uses. He says that you can actually boost the failure probability from polynomially small to exponentially small by using an error correcting code and sending it in a distributed manner. But why am I saying this is n log n? I didn't even change stage broadcast. Everything is still log n, and the communication is at least n log n. It turns out that when you have a failure probability that is exponentially small, you can divide the players into groups of size log n. So there will be n over log n groups. And what you can do is you can run this protocol over the log n size group. So all the n's will now become log n. Earlier you were broadcasting log n times, now you'll broadcast log n times. Earlier the code word was C from n to 10n, now it's log n to 10 log n. And now the failure probability is polynomial instead of exponential. But this polynomial probability is enough to union bound over all the groups. So what you can do is by taking groups like this, you can only broadcast log n times per player and still union bound over all the groups. And therefore the total communication in your protocol is n log n. And this is Gallagher's improvement. At first, it may seem that this protocol is also resilient to malicious players. And this is because one may think that in stage broadcast, players are just broadcasting independently. So clearly malicious players should not affect this. In stage guess, players are just guessing independently. They're just taking all the copies and seeing which one is the majority bit. And this should not be affected by the malicious players. And in stage boost, you're using an error correcting code. So even if there is a constant fraction of malicious players, no big deal. You just have a larger distance and the malicious players can go into the distance directly. So it's not easy to see what breaks. It's actually very subtle. But what really breaks is that in stage broadcast, the players may not broadcast what we call pure bits. When you have an honest player, then its input is either a 0 or a 1. And if its input is 0, then in stage broadcast, it will broadcast 0 log n times. And in stage, if its input is 1, then in stage broadcast, it will broadcast 1 log n times. Now, a malicious player is not required to do this. What the malicious player can do, for example, is that it can broadcast 0 half the time. So let's say every odd round it broadcasts a 0 in stage broadcast, and it broadcasts 1 the other half of the time. Now, when this happens, and the other players do majority-based decoding in stage guess, then they are equally likely to decode 0 or 1 because it just broadcasted 0 half the time and 1 the other half of the time. So any other player in this group may decode to 0 with probability half and may decode to 1 with probability half. And therefore, half the players in this group will decode this bit to 0 and half the players in this group will decode the bit to 1. And when they send this encoding, then half the players will encode something that has 0 in the place of the malicious party, and the other half will encode something that is 1 in that place. Now the error correcting code starts to hurt you. Now the fact that you took an error correcting code and you're encoding different things means that you're sending completely random coordinates. And these random coordinates will not allow the failure probability to go down. They will not allow any boosting to happen. And that's where Gallier's protocol will break with malicious players. They will broadcast a mixed strategy where they'll broadcast 0 half the time and 1 half the time. And then these encodings will be for mixed strings. So some players will be broadcasting a string with 0, some players will be encoding a string with 1. And then no boosting will happen. You will not get the boost in the failure probability. So you will be stuck with the trivial protocol, which requires you to go log n times in stage broadcast. Okay, that's the problem. And it actually is not due to the fact that you're decoding by majority. It may seem that all of this was possible because you know that the players will decode by majority. But even if you pick any other threshold, even if you say that if you get more than 30% of the ones, then I'll decode to 1, and otherwise I'll decode to 0, the malicious players in stage broadcasts will just take that threshold as the number of times they broadcast as 1. So if you were to decode based on 30%, then the malicious player will just say, okay, I'll just broadcast 1 30% of the time, and I'll broadcast 0 70% of the time. And again, you have an equal probability of either getting a higher or a lower fraction. And again, you will send different strings and everything will start breaking down. So how do we fix this? Well, we observe that when you do not have malicious players, then this guessing in stage 2 was actually helping you. And it was helping you because in stage broadcasts, a player may either broadcast either all zeros or all ones. Let's say it broadcasted all ones. Then any other player in the group will receive, it will have some noise, but most of the bits that it receives from this player will be ones, and only a small fraction will be zeros. And what you do by guess is you decrease the error. You had most of the bits to be 1 and a small fraction was zeros. And now what you do by guess is when you do a majority-based decoding, now everybody has all the bits to be 1. So it decodes it to 1 exactly. And in the other case, when most of the bits are 0 and some of the bits are 1, it decodes it to 0 exactly. And so guessing makes the estimate more close and more exact. But if you have a malicious player, then guessing actually makes it worse. You earlier say a malicious player was broadcasting 0 half the time and 1 half the time. Then when you guess, before you guess, every player receives a count that is approximately half zeros and half ones. But after you guess, half the players are at one extreme, which is at absolute 0, and half the players are at the other extreme, which is at absolute 1. So guessing is actually making it worse for malicious players, if there are malicious players. And our approach is to actually just delay guessing a little bit. What we want to do is we want to run stage broadcast. This time we will have root login rounds because the calculations will reveal this parameter is optimized at root login. But we will not immediately guess because guessing takes us farther. We'll first try to boost it. And this is still a problem because now you're boosting something that is not exact. It is not a, it is, you have no guarantee that all the players will be sending the same thing. But what you do know is that if you boost before you guess, then all the players are boosting things that are approximately the same. And we will use this. We'll define a new notion of error correcting codes that is called locality sensitive, that can even boost things that are approximately the same. And once we have boosted it, we have a probability that is polynomially small. We will all guess and everything will be correct because now we can union bound. Okay, so this is the overall idea. Let's go over it one more time. You have stage broadcast. Each party just broadcasts its input root login times. At the end of this, the players have root login copies of each party's bit, and it computes a count, which is the number of times it received a 1 versus the number of times it received a 0. Now, we know that these terms are close together because the noise will only change a small fraction. And we do not guess because it makes it farther. What we do is we use the fact that these towns are close together, and we use a locality sensitive error correcting code to boost these towns themselves. And now they're closer with very high probability, except with probability polynomially small than n. And now that we have these boosted counts, we can guess and we can use the union bound technique. Okay, so everything boils down to constructing these locality sensitive error correcting codes that work even when the inputs are close together and not exactly the same. So let's define them formally and see how to construct them. Now, in a classic error correcting code, you have a picture that looks something like this. You have the strings that you want to encode. These are, let's say, all bit strings on n bits. And what an error correcting code does, it takes these n bits and it gives you a slightly larger range, let's say 10 n bits, such that the encoding of any two bit strings is now far apart. And they differ in a constant fraction of the coordinates. So this picture looks sparser. What we require from a locality sensitive error correcting code is something stronger. From an error correcting code, we wanted that as soon as you have two strings that are different in one coordinate, your encodings are wildly different. Here we want to respect the distance in some way. If your strings are close together, let's say they are in this yellow rectangle, then the encodings will also be somewhat close. They will be in this yellow rectangle. And if your strings are far apart, let's say this string here, the bottom left and the top right in the yellow and green, then the encodings will be very far apart. You have a yellow rectangle, it will be somewhere here, which is far, and the green thing will be somewhere here, which is very far from the yellow rectangle. And this is what we want. We want close things to be mapped to close because our counts are guaranteed to be close, but not exactly the same. And we want far things to still be far apart because we want to boost the probability. Now, this picture is actually oversimplifying things because what we know is we have the triangle inequality. For example, we know that if these two things are close together, then these two things are also close together. And you cannot have such a neat separation. You cannot have these clean rectangles such that all these images are far apart because what for all you know, maybe you're in this small rectangle here. And then for this rectangle, the strings are very different. So care needs to be taken in defining these the right way. But the high level intuition will be that if your strings, which will be your counts, are close together, then the images will also be, the encodings will also be close together. And if the strings are far apart, then the encodings will be far apart. Okay, so let's see how to construct them. Well, our construction is showing simply that if you take a random linear combination of all the counts of all the coordinates in your string, then you get something that is locality sensitive. Why is that? Well, firstly, what we want is if your strings are close together, then your encodings are close together. And this is simply because of a Chernow bound. If you take each coordinate in your linear combination randomly and independently, and all the coordinates are close together, then the sum will also be close together. The error will converge and you will get something that is close. So this part is simply a Chernow bound. The other direction is more involved. And here what we want to show is that if you have two strings that are far apart in the L infinity sense, so there is a coordinate where the strings differ a lot. Let's say they differ by delta. Then this linear combination will also be different by approximately delta up to constant factors with constant probability. So let's see how this works. You have two strings that are far apart, and there's one coordinate where they're delta apart. So let this be the first coordinate, and let all the other coordinates be the rest of the coordinates. Okay. Now, it is either the case that the random linear combination, when you only consider the remaining coordinates, not the first coordinates, then it's either more than delta over 2 with probability more than 1/2, or it's less than delta over 2 with probability more than 1/2. In the first case, when it's more than delta over 2 with probability more than 1/2, whenever your random linear combination does not take the first coordinate, which happens a constant fraction of the time, then you get a linear combination, then you get a value that is at least delta over 2 in the difference, which is by just our assumption. If the remaining coordinates is something that is delta over 2 apart and you don't take the first coordinate, then the overall thing is also delta over 2 apart. On the other hand, when the remaining coordinates give something that is less than delta over 2 apart, then with constant probability, you take the first coordinate. And this coordinate is delta apart. So if you were inside delta over 2 in absolute value before, then if you take this coordinate, which happens with constant probability, then now you're outside delta over 2. And in either case, there is either you take this coordinate or do not take this coordinate. There's one setting where the value of the linear combination is more than delta over 2 apart. And this is the claim here. We get something that is like the infinity norm with constant probability. And when you plug this in, you get a definition of locality sensitive error correcting codes, which we can use the boost accounts of our protocol. And we get something that is en route login and solves bit exchange in the presence of noise and malicious parties. So that's it. That's my talk. Thanks for listening.